With any asset management system, the first thing you do is you talk about or you assess what you have. So going back to 2008, this is kind of where we were at. New York State highway system has 16,600 centerline miles of highway, 8,000 centerline miles of that's on the NHS. The rest of it is off the NHS. That doesn't count the local system. The local system is much bigger, but we don't collect data on the locals, so I'm not going to address it here. In 2008, I was hired in 2006. In 2007 and 8, New York State DOT staff developed the pavement preservation model. It was a basic, very basic pavement management system written using VBA and SQL in MS Access. It was our first attempt. Actually, our first attempt was in Excel, and it crashed everybody's computer, so we switched it to Access. What it did, though, is it mined existing data to develop deterioration curves, decision trees, and some very basic optimization. And it worked within the existing New York State DOT data structure. That came with good things in that we could implement it quickly, but it also has limitations, which I'll get into soon. There we go. New York State has a very rudimentary way of assessing its pavements. The first major piece that we use is a surface rating, which essentially measures cracks. I don't know if you can see my... No, you can't. Well, that's all right. In the upper right-hand corner, you're going to see pavements that we call excellent. They're scored 10 to 9. 8 to 7, those pavements are good. They have some cracking, but it's infrequent. Usually the joints are starting to open up at that point, but nothing major happening. 6, we label those as fair. So if you rate a 6, it's fair. We have frequent cracking, and it's mid-level in severity. It's not too bad, but it's bad enough where you really can't do a microsurface and expect it to last. And then lastly is poor. Poor pavements are usually rated anything 5 or less. New York State also has a weird thing in that we use a 10-point scale for our pavements, but almost all of our pavements go from 4 to 10. And 10 and 9, the only distinction between a 10 and a 10 is brand new, and a 9 is 1 year old. That really is the only difference. So you could boil our system down to 5 condition states, but we love 10 points. It allows our averages to stay up above 7, which is good. The other thing that we collect besides the cracking, just the general cracking index, is the dominant distress. These are things that you can see from a windshield survey that would indicate to you that there are problems with your base or your subbase. Those include alligator cracking for asphalt pavement, spalling for PCC pavement, which is a different kind of a failure mode, and widening drop-off, which usually is used for PCC with asphalt on top. In New York State, one of the things that we did is when we did a lot of overlays on our existing PCC network, we widened the roads. And when we did it, if you had to widen the road 3-4 feet, we usually did it all on one side of the road. And so what that does is it looks really good, and then eventually you have 2 different structures underneath the pavement, and they deteriorate differently, and you get that difference. And it's really tough when you're driving because it kind of wants to pull the car off to the curb. It's very dangerous. So we track that separately. And what these do normally is they denote, at least in the past, you have to do something more substantial at this location in order to address all of the issues. There we go. So as I mentioned, this is our basic pavement surface rating. The nice thing about the surface rating, though, is it relates to general work categories. So if there's no cracking, you don't have to do anything to the pavement. If there's a little bit of cracking, you do crack seal, and you see it goes through PM, rehab, major rehab, and reconstruction. This worked well for us for years, but like I said, it's rudimentary. It doesn't really get to the heart of the overall complexity of pavements. So we started to develop this model, right? And the model itself pulls in things like the surface score and the dominant distress, which we collect annually. But now we were also collecting IRI. We're collecting roughness, rutting, faulting, other information. That information had to be incorporated somehow into our decision making, or else why collect it? If we were only going to do it as a reporting exercise, that's only half of the thing that you're trying to do. The other half really is to use that data intelligently to make decisions. And the last big part of that was AEDT. Obviously, traffic matters. But we'll get to that in a minute because the traffic doesn't matter the way you think it would. There we go. So unlike Texas, which I think has 2,000 deterioration curves, we have 45. I just like to think that ours are better. So we have 45 distinct deterioration curves for surface score, and they're based on data going back to 1981. We did a lot of statistical analysis on all that data to determine key performance factors, what affects the deterioration of the score, what affects the propagation of cracking. We found that the location in the state matters, not just because of the difference in the weather conditions, but also in the difference in the topography. So, for example, on Long Island, it's wet down there, but there's a lot of sand and sandy soil, so the water is free to drain in that location. Up north, where we have severe freeze thaw up in the Adirondack Mountains, it's also mostly bedrock. You have excellent soils up there, and so it's much stronger. What that means is that the pavement will deteriorate very quickly to a fair condition and stay fair for a really long time. It takes a long time to get to pour. Downstate, down on Long Island, it's the opposite. Pavements stay in really good condition, and then they drop off very quickly. Most of that, though, is due to the massive truck traffic. The other things that we found that affect deterioration, oddly enough, is the pavement type, but the work type category. So what work did you do last time? If I did a thin treatment, they deteriorate differently than a reconstruction. And what was the condition of the pavement when I did that work? So if I do a thin treatment on a poor pavement, it's not going to last very long. If I do it on a good pavement, it will last much longer. We also did a similar analysis for IRI. We took a look at IRI propagation and deterioration over time. Now, the one I'm showing here is what you would think of as a classic deterioration curve. It actually looks like a curve. But because New York State only uses whole numbers in our cracking index, that's not really how you do it. It's actually a step function. So our pavements aren't rated a 5.2. They're rated a 6 for a bunch of years, and then eventually somebody uses their expert judgment and says, now we're poor. It's a 5. Then it'll be 5 for a bunch of years. So I don't know if you can really read that on the bottom, but this is one of the deterioration curves from our model, and you'll see that a pavement will last 1 year at a 10, 1 year at a 9, 2 years at an 8, 7 years at a 7, which is good, 9 years at a 6, fair, and then 12 years at poor, and then anything after that is just junk, right? Right, essentially, yes, it will last forever in junk status. But that is essentially what we're dealing with here is a step function, which, like I said, is different from what other people are used to, because there isn't really a curve to it in the classic sense. We take other stuff into account, inventory and road characteristics. We have a lot of information that we look at. We make exceptions, so the model will come up with a treatment type, and then we'll take a look and go, well, if there's curb there, you don't want to put a 3 or a 6-inch overlay where there's curb because you lose your curb reveal, and it'll make other recommendations. That's an example of one of the things that we do. We also do regional cost adjustments. To do work in New York City is extremely expensive. To do work in the middle of nowhere is not. So we take that into account, and we can break it down county by county. Like, for example, we have a region 8. It's the Hudson Valley. It goes anywhere south of Albany all the way just north of New York City. Well, a couple of those counties, Westchester County, extremely expensive. The Dutchess County, there's a bunch of farms up there, very cheap. We're able to make those distinctions within there as well. And this is broken down. Now, when we do the analysis, when we first put this together, we created a decision matrix, which I noticed you guys are going to a matrix idea for structures, and I love the idea because I apparently love matrices. But one of the things that you'll notice here is there's 2 dimensions to it. There's actually 3. If you see at the top, this is a matrix for asphalt and overlay pavements with an AADT between 8 and 20,000. One of the things that we found when we did the analysis is that the actual traffic volume does not really affect the deterioration rate of the pavement. It's weird. You wouldn't think so. But the pavements were designed to handle the truck traffic that was on them. We haven't had major swings in truck traffic since these roads are built. However, it does affect the treatment selection, and that's where, at least in our model, that it applies. If you have a lot of truck traffic, a lot of volume, you want to do heavier treatments to get the same performance. So instead of getting on the front end, we get on the back end. One of the other things I want you to notice is that for a given cracking value, so let's say for poor pavement, if there's not a lot of roughness, we say you can get away with a mill and fill. If there's a boatload of roughness, if it's very rough, that means there's other issues there, and you need to do a thicker treatment in order to handle both the cracking and the roughness. So this is a nice, easy way to display it instead of having a decision tree with a whole bunch of branches. So the model makes an initial recommendation. Treatment windows are important. When you don't actually have a deterioration curve and you're going to be in fair condition for 8 years, you don't want to do a treatment in the first couple of years that it's fair. You want to save your money and kind of get it at the back end of the window. You've already lost the dollar value. You went from, let's say, a thin treatment to a multi-course mill and fill. There's no point in doing that early. Let the pavement ride out for as long as you can and then do it later in its life. And that is also taken into account. And lastly, as I mentioned before, there's a bunch of exceptions and modifications to the initial work recommendation. There we go. Like any good model, it can model future conditions. The model processes the year's work plan, including all the individual projects that come in from our project support system. So these are the committed projects. Plus, it makes recommendations. All pavement segments where work was done, the cracking index goes to a 10, totally clean, no cracks, and the IRI drops to a 70. At locations where work was not done, we deteriorate everything down that step function curve, and the roughness goes up accordingly. Now, I like the existing system because I had a very strong hand in writing it and making it. However, it does have some severe problems. The first is that we have multiple ways to locate projects, and this is a department problem when you look at it. We have our maintenance and safety data relies on things called reference markers, an actual signpost in the field that has a bunch of numbers on it to denote what route you're on and some other stuff. And nominally, they are placed every 1/10 of a mile. But they're not actually placed every 1/10 of a mile. They've been hit by snow plows. They've been replaced. They're just missing. So a person in the field looks at that and goes, I don't know what route mile point I'm at, and therefore I can't figure out what my cracking value is besides just looking at it. But I don't have any historical data. It's tough getting those two things together. The roads and highways solution is going to solve that problem. The second big problem is the existing surface score performance model is a step function, which I'd mentioned before. The third, project selection and benefit calculation, we mentioned this earlier today, is instead of having a benefit calculation area under the curve, because we don't have curves, what we do is we prioritize the work by sending order of the ratio of the dollar it costs to fix the road divided by the VMT of the traffic on the road. So get the cheap projects done, get the preservation done where a lot of people drive, and you're going to get the best bang for the buck. However, that doesn't really relate back to the way that modern pavement management is done. So we had this jump that we had to take care of. The current roadway inventory system doesn't perform dynamic segmentation very well. So every year we have, as I mentioned before, about 16,000 centerline miles. That translates to 40,000 different pavement segments. If I wanted to roll, and it breaks on any inventory change. If I wanted to roll those up into things that really are meaningful for pavement management, the system can't handle it. Our existing system cannot do it. So I annually would do that by hand. It stunk, and I hope to never have to do that again. The process to manage program projects is very cumbersome because we're working in an access database. So it's not as simple as just pulling data in, putting it in the database, and hand it out to everybody. There's access regulations. So if we have 11 regions, what that essentially means is we would distribute 11 separate copies of this access database for people to use. It stunk. And the system can tell what conditions can be achieved from a given budget. So I put the budget in, it gives the conditions out. I put the budget in with a specific strategy, it tells me what I'm going to get. But it can't go the other way around. I can't say, meet these condition requirements and tell me what the cheapest solution is. It can't work that way. There's too many permutations. It just doesn't run. So that being said, this is where we were at when we hired AgileAssets to come in and implement the enterprise asset management solution. And for all the solutions to our problems, I'd like to introduce Ting Wang. He's going to talk about how he helped us.
So, AgileAssets to the rescue. As Scott has mentioned, I'm Ting and I'm from AgileAssets. So in the second part of the presentation, I'm going to touch some highlights in the New York pavement implementation. As you can see, some of them are new processes because these were brought in as we are implementing the pavement management system. One of them is the existing process. We basically replicate the old performance modeling and decision tree because some of them are valuable and we want to preserve that process. All these are brought in because we want to increase the work efficiency and trying to build a better pavement program at New York. So the first one is RS and the Roads and Highway Interface. As we have covered this many times in this conference, have a good RS is the backbone of building a good pavement management system. In New York case, we actually have a pretty good RS. It's called a Mile Point Network. It's maintained by the state highway data services. It's a county-based route system, meaning that a big route like Interstate 87 is actually considered different routes when it goes across different counties. Also, worth noting is that it covers all the public roadways in New York State, and the route measures reset at the cross county boundaries. we will. Another thing is that the route ID is actually the route directions is built into the route ID, and New York DOT is one of the state that has implemented the Rosenhow Highway Interface, S34 Rosenhow Highway to manage their RS. So we also set up the Rosenhow Highway Interface to hook up the Rosenhow Highway, so we can update all the events in our AgileAssets application. Everything sounds very good, but there's always a but. So the route ID in route name in this case in New York is an unintelligently recognizable 9-digit number, meaning that as an regular end user, when we want to pick a route name, there's no way you know what you are gonna pick. For example, I-87 in Albany County, it's a number like 1000589, something like that. So to solve that problem, we built a second LRM in our system. This, in a sense, this LRM expands that 9-digit route identifier to 4 human-readable but still contains essential information fields. These fields are roadway type, roadway county, roadway direction, and the roadway description. This is a collaborative result between AgileAssets, Pavement Program Area, and the Highway Data Services. So the idea of building these 4 fields is that as the user enters the record, when the user enters record in the roadway county, the available options in roadway, as the user enter records in the roadway type, the roadway county is gonna get filtered by whatever you have entered. And as it goes on, the roadway direction and the roadway description gets filtered as the user enters more data. The most important part in here is the roadway description. It contains very concise but very essential information to help the user to pick up the exact road ID the user want to select. And this LRM, although this LRM is not built in the Rosenhow Highway in NYSDOT, but we build this LRM in AgileAssets to be fully compatible with the Rosenhow Highway Interface. So whenever we run the Rosenhow Highway Interface, this LRM is going to get updated as well. This is just some, I don't know if the picture is, the graph is big enough, but the idea is to show that in the roadway description, even if you enter the same text, because we have used different because we select different roadway types, the options that the user gonna see is actually different. It helps to limit the available options, so the user it's very easy for an end user to pick the correct route identifier. Also, want to highlight is that this roadway description does not just include the actually the route number. Sometimes a big route like New York State Route 20 or State Route 5, when it goes into the city, it actually has a city name, has a regular name of the street, like Main Wolf Road or Central Avenue. This description also includes that. So basically, as long as the user knows any information about the road you are working on, just type that, you will get the road. And this is an example of roadway type road. Road in New York is basically the local roads, because in the future we have the plans to expand the system to include local roads and ramps. So we want to build this LRM to be able to be used by local municipalities, so they will be able to pick up the routes as well. So not just the state numbered routes. The next highlight I want to say is the performance indexes and the decision tree process. As Mike has mentioned, the main performance index used in New York is called service score, and it's a step function. The performance model is a step function, and it basically says the number a segment will stay at a particular score for a number of years, and this duration is determined by the current score, last treatment type, climate region, and the score before the last treatment. If you are the user of our pavement analysis, you know this is not a typical performance model that application can handle. But through the calculate column and calculate column Groovy, we were able to fully implement this performance model. And in addition, Mike has mentioned the decision matrix that was originally implemented in the access model. We were also able to convert the decision matrix to decision tree and fully replicate the existing decision process in the new system. The next highlight I want to touch is the benefit calculation and the project selection. As Mike has mentioned, the existing process, we list all the prospective treatment, we calculate their costs, and then we determine the ratio of the cost by cost and the VMT, and just list them in a descending order, and we pick the project with lowest dollar per VMT. If you think about it, this is not a performance-based project selection process. It implies that all treatments will bring your segments back to the perfect condition, and then it will deteriorate in the same rate. But we know that's just not true. So together with this new implementation, we now use the benefits. We will use the benefits as the new project selection criteria. Just to refresh our memory, benefits is the area under the performance curve. Even in service scores case, we can still plot it as a curve. It's just a step curve. So in this case, we were able to calculate the area under the performance curve, but also we also include the threshold for the benefits. So we don't want to include the service score that has 99 years of lifespan, basically the junk part of the performance model. So so we include the benefits as the project's selection criteria. That's so we will be able to fully utilize the analytical function of the pavement analysis. Also, we will include we will use instead of ranking or prioritization, we now use the full optimization to select the projects. Another benefits coming with this new implementation is now we can do bi-directional analysis. With the budget level, we can tell you the network conditions. And also with the network condition, we can tell you how much budget you will need. The next highlight I want to talk about is coming with this new implementation, we brought in the new pavement management sections, the process to develop pavement management sections. As Mike has mentioned, in the existing process, we basically the model just import a set of sections from the roadway inventory system RIS. But the problem was that First, there are some issues with the dynamic segmentation in RIS, and also RIS is an external system to the pavement program area. Therefore, pavement users doesn't have any control on how those sections are generated. So keyword of this highlight is that now the pavement users have complete control of how they want to generate the pavement sections, and will be able to make changes to it whenever necessary. So in the new process, and this is we have after the discussion with pavement program area. So the first one is that the first step is we use the existing pavement management sections, inventory sections, and the last year's construction to do a finance partition. So then we generate the intermediate table, and then we use the condition survey data and the inventory attributes to update all the needed fields for in this table. Then we do a dynamic aggregation. Basically, if any of these fields are the same, then we stitch them together. Also, we exclude the bridge sections from this section, because in New York's case, when we do pavement planning, we are not doing any treatment on the bridge. So we get the intermediate dynamic aggregation table. At the end, usually in other clients, we usually stop here. But in New York, we add an additional step at the end. Basically, we want to do an additional aggregation using the service score, because service score right now is still the main performance indicator. So we write an Oracle procedure to do the additional aggregation, and then now we have the final management sections. Remember, even at this stage, the pavement user can still make changes to this result, and at each step, pavement users will be able to change them, and that's why the highlight I want to bring to this one is the now complete control. The last one, but not the least one, is how we bring the new process to manage the program projects. As Mike has mentioned, the current practice is that at the main office we import the projects from an external system called Program Support System, or PSS, and then we make 11 copies of this access model and distribute it to the 11 region. Region make updates to the program projects and send the update work plan back to main office. So with the implementation of the new PMS, we were able to streamline the whole process, and with access regulation, we were able to manage the whole process within the same application, same window. So the keyword here is streamline. This is the high-level diagram of the new process. So basically, the main office still imports the programmed projects from PSS through an interface. Then we make necessary changes. Again, all these are just system functions we already built into the system. It's all already there. And then some of the adjustment including costs, because some of the costs from PSS including the cost to fix other parts like the sidewalks or drainage. And or some of them we need to move the projects a little bit. Then we copy this updated work plan to the regional work plan. Region run their analysis, make updates to the work plan, and then at the end, the main office collect the update regional work plan and then develop the statewide final programmed projects. All these are implemented in the application without any customized work. It's all about just the purely configuration. So I was the several items I just touched just some highlights of this implementation, and which I think it's all about. I think it's the unique parts of the New York implementation. Of course, there are many other things in a pavement implementation, such as how we calculate how we aggregate the data in network master, how we implement some other regular performance indexes such as IRI or forwarding. But all those are, I think, every pavement user client of AgileAssets knows how to do that. But so this is just some unique features in New York implementation. But there are still some next steps in our pavement work. The first one is we want to New York is right now in the state of using automatic pavement collection to address the requirements from Map 21. That will bring in new performance curves and performance, and that may also bring changes to the decision trees. The second one is that we're going to develop a new performance index called PCI. As Mike has mentioned, that the current surface score only mostly address the cracking issue. It doesn't really address a lot about the riding, like faulting, rutting, or IRI. But in this new pavement condition index, it will include the factors about cracking, roughness, rutting, faulting, and dominant distress. The third one is as NYSDOT is going to replace the program support system with the new software called Oracle Primavera Portfolio Management. So we will need to develop the new interface with the new software OPPM, which is a PSS replacement. So I want to conclude our presentation by talking about some of the takeaways. This is when we looking back about this pavement implementation, we think it's a pretty successful project. The first one is the pavement program area is very open and progressive about adopting COTS products and processes. I think this is the most important part which is when we come to an agency and convince them to do a fast project delivery and build a better pavement program. The second one is AgileAssets has been working closely with all the involved program areas. Remember the second location reference method, LRM. This is I think that's a good example of the collaborative work between AgileAssets, Highway Data Services, and the pavement program area. And we, in the new MMS implementation, we found that the MMS group is very welcome with this new RM as well. The third one is that whenever we were presented with a challenge, both AgileAssets team and the program area are willing to work together to address this problem and willing to find a common ground. And both parties are willing to make compromises if necessary. And the last one is my shameless advertisement, is that pavement analysis is a powerful tool with a great deal of flexibility. It is really amazing. With that, I thank you for your time and welcome any questions.
Okay, we certainly have time for questions for Ting or Mike if anyone is interested.
Okay, so that's maybe a question for Mike to start. I think I have two questions, but so the first one, if you compare, so you've already run scenarios with the new PMS. How did that did the results compare to the old one?
We have not done that yet.
I did a test run, so what?
We have not. He has.
All right, that was a question to you, so I don't. No, go ahead.
We did a test. I did test run using the old method and the new method. Yes, because well, of course we missed a lot of the details in this presentation. So when we say benefits, it's not just benefit, including it actually putting corridor importance factors, as Steve mentioned in the morning, and we also take into the account of VMT as well. So we did the we call that five color bar chart, basically the distribution of different pavement conditions using the old method and the new method. The new method is much better than the old method. When we want to maximize the benefits, you can see the conditions, the pavement, the distribution of good, excellent pavement, good pavement is much more than the old one.
Okay, excellent. And then second thing, so in your current existing process, the regions make the decisions, right? So do they have different, no?
No, please continue.
So, I mean, they were running their own, you said they have to come up with work plans,
yep.
Right? So how do they come up with work plans? Do they use the tool that you give them? And what's the future?
Yes, and yes. So let me expand on that, and I think Steve brushed up against this a little bit this morning.
Oh, sorry.
Thought it was loud enough. Hello. All right. So what we do is we will run the model centrally to determine a preservation need for each region. So we run the models unconstrained. We find out what the preservation needs are for both for bridges and pavements, and then that becomes the cornerstone of the regional allocation, and we hold them to that percentage. So, for example, if statewide, I'm just going to take pavements because I know pavements. If statewide we need $250 million in preservation spending on the pavement system, but we can only afford 200. Everybody hurts equally, but everybody gets an equal share based on their preservation need. Then we tell them, you have to come, and when you do your preservation, or when you do your program, you have to spend that much money on pavement preservation. Mm-hmm. I don't care where the selections are, as long as you're spending that amount of money in an intelligent manner. So we deal with it on the front end as part of their program update submissions. Then, after every construction season, we look at the projects that they actually delivered, which is different than what they said they were going to deliver. We compare those locations and the work that are done there against the model recommendations, and as long as they're in the same curve family, so your PM is PM. I don't care what PM treatment you use, but do something PM-ish here. If you're doing that, then we're good. And we actually rate and track how often the regions deviate from the model recommendations. And that has allowed us to do two things. The first thing it does is it educates people and say, listen, guys, you're going heavy everywhere and you're not getting as much done and your system is suffering for it. Or, in some instances, it has made us take a look at the work recommendations that the model is coming up with and taking a look at maybe changing those. Because in the end, if the model can't just be the end-all and be-all, it is the representation of the collective unconscious of all the good engineering that we have in the department. And so if there's a lot of say that says, listen, you really shouldn't do that here, you should do this, we'll take a look at that. And so it's kind of a two-way street as far as that goes.
What we're doing, Pascal, is these guys run the models. We find out what conditions are achievable.
Right.
So we hold the performance measures, percent BNT good and excellent, backlog, and percent poor. So we know that's achievable. They could run the same models, get the candidates. They put a program together. They've got to hit, what, 70% of the...
Right, 70% of the total, yeah.
So they don't have to hit the theoretical perfect metric. They hit something that's 70% of that. Then in reality, when we evaluate the program, if they're at 90% of the 70%, we accept their program.
Right.
So in the ballpark, it's practical, it's reasonable, but it requires them to do, a reasonable amount of data.
Right. And they are forced to run the models on their end because the cornerstone of the submission is the output from those models. So at the very least, they have to run it to see what the conditions are going to be, to give us those in the format we demand. And that loop makes somebody sit there and actually run the model, which is good,
Thank you.
You're welcome. Any questions for Ting?
I'm good here. Still for you, Mike. I want to check with you guys, how you guys manage the construction history database.
Okay, that's a good question. So, So right now, because we do an annual windshield survey, we essentially have 11 different regional teams that drive all the routes in their region. They can take a look at the score from last year and they go, whoa, there's no cracking here, right? Cool. So that means that work was done. It is their job to go and find out what was done. Now, one of the things that we have instituted, because regions and also our state government likes to say how much work that we've done over the course of a year. If a region, let me get the timing right. If our windshield survey is done, let's say in May or June, and the construction was done in August or September, what the region can do is they can alert us and say, this project was delivered, it is completed, it is final, it went from here to here on the linear referencing system, and it was this work type. If they give us that information, we will credit that in the system, and then the score will go to 10, et cetera, and that gets done in our roadway information system now, and will be done, hopefully, as part of the new business process in Agile when we go to the new automated distress collection. So if you have a bunch of linear feet of cracking that was collected last year, and all of a sudden you have no cracking in the same piece of pavement, work was probably done, because pavements don't heal themselves, and we'll have the same kind of a feedback loop. The regions will have to let us know. We're also instituting other ways to get the data into the system. One of the things that we did is we set up a window interface and an access regulation for our resident engineers in each county, our maintenance guys. If they know a project was done, they have the opportunity to go into a special window that actually lists the locations by reference marker, because that's what they know. They don't know route mile point. They know reference markers and things like that. They can put in from this reference marker to this reference marker, I did this work type. And then that gets checked in the main office to make sure, and then it gets approved and put into the work history. So right now we have a couple ways to get the information in. Like I said, when we go to automated distress collection, that's going to have to be more formalized because you're not going to get that same feedback as quick, as far as I'm concerned. I think there's going to be some other issues we're going to have to work with, but I don't know if that answers that.
Sorry, do you guys have any future plans, say, like automate this process? Because I think most of the work for the construction history probably is manually inputted.
Yes. Yep. One of the things that we have tried to do, at least what I hope to do, and I don't know if OPPM is going to support this, is the problem. I don't know enough about OPPM to know what it does. I know a lot about what I'm told it doesn't do, if that makes sense. But what I'm hoping is that we can get printouts on the LRS of the work that was delivered and recorded in OPPM. Now that's going to work for our capital work. It's not going to work so good for our vendor placed paving program, which it doesn't live in OPPM. So then we're going to need that manual that manual input, just for that part of the system. Now, you would think that wouldn't be a big a deal, but more than 2/3 of our lane miles of work right now are done through that VPP because we don't have enough money to do the capital work anymore. So yes and no, right?
Absolutely. Thank you so much.
Sure.
We still have a couple of minutes. Anybody else?
I have a follow-up to that.
Absolutely.
That was good on getting construction history moving forward. How much of the historical data do you have from the underlying structure when it was built, the layers and thicknesses?
Now, here's my answer. My answer is reliably we have the last work type, and reliably we have the pavement type. Right. So, and the last work year we have that too. But before I got to the DOT, so not my fault, we went from one major system, which we called the mainframe, and we brought that over into another system. And when we did that, a lot of the codes that we used for the underlying structure got scrambled up and were never fixed. So depending on where you are and what subset of the system, that data is not as reliable as it could be. Let's put it that way. To the point where I don't feel comfortable using it to make decisions. Recently, before I was recently promoted to work with Steve, one of the big things that I was going to work on was fixing that, going into the construction plans and finding out what was actually done at a location. But that's a lot of work, and I didn't have any staff. So oddly enough, I didn't get it done. So,
Thank you.
You always said you're going to move to PCI.
yes.
So does that mean you're going to have more variables, right? You're going to be collecting a lot more things.
Well, it's funny. We're not going to be collecting more things. It's all going to be stuff that we collect already. But right now, we don't. So for benefit right now is just the cracking index. The difference in the cracking index over time multiplied by the corridor importance factor multiplied by VMT, whatever. But what I want to do is I want to get a PCI value, which now will take 35% of that value will be a cracking deduction, 35% of it will be rutting, and then roughness, then you'll have rutting and other stuff. So it's data we already have, but now we're going to use that to kind of drive metrics. And this is really important, not so much for the pavement management system, but for when you're doing cross-asset trade-off. Because when you're doing cross-asset trade-off between the bridges and the pavements, you got to show what your total benefit is. And my total benefit to the driving public is all of those things, right? And the total benefit on the structure side is not just that my MBI rating went from a 2 or a 3 to a 7. It's not the same. There's other stuff involved. A bridge that has 200 cars a day on it, we should probably close that if it's in bad condition. If a bridge has 40,000 cars a day on it, well, that has a lot more benefit to the driving public. So that's going to also come into the benefit calculations as well. I don't know if that answered your question, but
Well, I was wondering if you were going to have a correlation issue with your old data, trying to get it caught up with your PCI, but it doesn't sound like you will.
no, but there's going to be a lot of math we're going to have to do in order to find out deterioration rates for each part of the PCI. So cracking deteriorates differently than roughness, which deteriorates differently than rutting over time. Like right now, I don't really know how rutting develops over time. I don't have enough historical data in a format that I can do that analysis or the time. But that's the next thing we're going to do is try to develop that deterioration curve. Right now we have a fake one in the
what you
system.
collect that fits into that with Agile software?
Yeah, that'll end up working out good. Yeah, because the data's in there, and this data keeps coherent history tied to the LRS in an intelligent way. Yeah, I mean, that's going to be a big deal for us. So.
All right. Thank you, Mike and Ting.